Okay, so now that we understand Newton's first law as F net equals 0, what happens when that net force or that unbalanced force is not equal to 0, or those forces are not balanced? In comes Newton's second law. So, two review points that we kind of discovered in class back when we were pulling carts and creating unbalanced forces were the following. So, review point number 1. When an object experiences an unbalanced net force, it accelerates. This leads us to Newton's second law, part 1. Newton's second law first states that the acceleration of an object is directly proportional to the net force that it experiences. That means that the acceleration and the net force will be of the same linear magnitude as well as the same direction. Okay? So mathematically, that means that the acceleration is directly proportional to the net force. Okay, and that little alpha-looking sign is a proportionality symbol you might have seen in math class. So that means they're directly proportional. Review point 2 was that objects with greater inertia or mass will not accelerate readily, and objects with less inertia or mass will accelerate more readily. So this can be thought of as like the difference between trying to push on a car versus trying to push on a bicycle. The two are different completely in masses, but the two are going to react to that force differently. The car is not going to accelerate very readily because it's so massive, and the bike will because it's not as massive. So that leads us to the acceleration being inversely, so 1 over mass, inversely proportional to the mass. That means the bigger the mass, the harder it is to accelerate, also known as the bigger the mass, the smaller the acceleration. Alternatively, the smaller the mass, the larger the acceleration, so smaller objects will accelerate more readily. If we put all this together, we get Newton's second law. The acceleration of a system equals the net force on that system divided by its mass. But usually, what you'll see is that F net equals ma. So they just rearrange the equation for the net force. Mass of the system times the acceleration in meters per second squared. So we're going to do 2 examples with this equation and this idea in mind, and learn how to solve problems in those ways. Alright, so example 1. A toy wagon is pushed with a force of 400 newtons in the east direction, and a friction force of 200 newtons acts on the wagon. If the wagon is accelerating at 2 meters per second squared east, what is the mass of the wagon? So our system here is the wagon, and we're going to use the idea of Newton's second law, F net equals ma, to solve this problem. Just like in our motion unit, we used a motion sort of a solution format. I've got one set up here for forces as well, so most of our force problems are going to be done using this format, and I will provide a template on the classroom for you to print out if you want to use it during your problem solving fun. Alright, so let's solve this problem first by drawing a picture of what's going on. So we have a wagon, however you want to draw it. It's being pushed by a horizontal force. This wagon experiences some friction, so we're going to draw a little bit of a rough road, and it moves in the eastward direction, east being positive in our case here, to also give our sign convention. What we do know is that the acceleration of the wagon is 2 meters per second squared east. It experiences an applied force because it's being pushed, okay, so it's a person pushing it, of 4.00 times 10 to the 2 newtons east, as well as a frictional force of 2.00 times 10 to the 2 newtons in the, yep, you got it, west direction. Because we know friction opposes the direction of motion. We're looking for the mass of the wagon, so that's our unknown, and we don't need to do any conversions here. So we've got our sketch, coordinate system, givens, unknowns with symbols, and we don't have to do anything with events. Alright, so that leads us to our interaction diagram. So we're going to draw an interaction diagram of our system. Our system is our wagon. And our system experiences an applied interaction with the hand or the person. It experiences a normal and a friction force with the ground. And it also experiences, like always, the gravitational force with the earth. Okay, that's it for the ID. Now for the force diagram. So, of course, our wagon turns into a dot. We have our normal force from the ground going up, and our gravitational force going down. Now those are the same size because the forces are balanced in that direction. I'm not going to accelerate in the y direction. Okay? I do experience a force of 400 newtons to the right from that hand, and that's 400 newtons, so that means 200 newtons, which is your frictional force, will be about half as long, more or less. Okay, and we need to state our convention. Positive going up and to the right, and our acceleration is to the right. Okay, because everything's east. Alright, so in order to describe the word representation here, what we need to do is say how the wagon is moving, which direction it's going, and why it's moving that way, including explanation of the forces involved. So what I'll write here is that the wagon accelerates in the east direction due to an applied force in that direction, which is greater than the friction force opposing it. Our assumptions here are we have a point particle system. Everything's a point particle, and we have constant acceleration. This never changes, which means there's a constant net force. Okay. And our estimation we can do in this case because we've got a pretty easy mathematical problem here. So we have 400 newtons east, 200 newtons west. That means we have an overall net force of 200. And then an acceleration of 2. So if we plug all that into this equation, then we get about mass of 100 kilograms. It's a pretty heavy wagon. So let's see how all that plays out now in the math. So there's a bit of a rhythm when it comes to solving Newton's second law problems, and I've kind of sort of laid out how to do these problems in that box there. So make sure you have this out when you're solving problems later on. So what we do is we write out the F net equation in the direction that we have acceleration. So we go F net, and this is accelerating x direction, so we have the forces in that direction are FA, take away FF. Okay, so that's our net force equation. And then for each net force equation, decide if the forces are balanced or unbalanced. And if they're unbalanced, set that net force equation to MA. So all of this equals MA because this system is accelerating. Okay, if it wasn't accelerating and those forces were balanced, then this would all equal 0, which is Newton's first law. Okay, so we rearrange for our wanted quantity, unknown quantity. Rearrange, and we can plug in. So that's 400, 200 divided by 2, which is exactly what we got, which with significant digits would be 1.0 times 10 to the 2 kilograms. Okay. The units work out because, let's just see the unit analysis. So a Newton is equal to a kilogram meters per second squared. It's a mass times an acceleration. Okay, so kilograms are equal to newtons over meters per second squared, which is what we did in the question, and then that gave us kilograms, so that works out. So we just finish off with a little sentence. Therefore, the mass of the wagon is 1.0 times 10 to the 2 newtons. Oh, sorry, kilograms. All right, good. Moving on.